tools, one of the things that was very clear is chaos had a tendency to stand opposed to one of our core values. LinkedIn tries really, really hard to make sure the member experience is as positive as possible. And while a lot of people think we induce enough chaos just by releasing new code, actually causing chaos in production seemed kind of scary to a lot of people. So we ended up developing something that we call linked out, and this allows developers to target just their own experience, to see what it looks like when a resource is offline just for them, but then also expand that out to the entire data center in incremental steps, whether it's just failure Fridays to make sure that everybody at LinkedIn knows what it looks like when this resource is offline, or it's testing an entire data center disappearing through some tragic means. Now, when we started talking about chaos engineering, I'm not a traditional software engineer. I actually have a structural engineering background. So the first thing that I thought of when we started this exploration was, what are the other industries doing? Not just internet industries, but what does structural engineering do? What does the aeronautics and space industries do? How do other industries deal with this chaos? What we found is that chaos is the result, or is the byproduct, of resilience engineering. What that means is, when I build a car, I'm going to try to make it as safe as possible. But I'm doing that based off of what I know the material properties of a thing to be, steel, aluminum, what the components are for this. And then I build an entire complex system, a vehicle, and then I don't just walk away and say everything is done. I have to take that car and usually put it at a high speed and park it very abruptly into a concrete barrier so that I can figure out what this looks like. That's not necessarily a different discipline. For other industries, it is part of the job of engineering to also test your code. Also test your vehicle. This is the same way that we deal with unit tests. It's the same way that we deal with integration tests. It's all the same. How do we understand what's going on with the system when it becomes complex? For distributed systems, and this is usually internet properties, economies, logistics infrastructure, it's really hard to have one person be able to say, I'm going to make this small change. What is the large impact to the entire system? So at least for our jobs, resilience engineering and chaos engineering tended to separate out as a way to make sure we could focus appropriately on these individual disciplines. Now, in order for me to fully go into why chaos engineering can be safe, or how chaos engineering can be safe, we need to talk about what resilience engineering is. Resilience engineering starts with a steady state. For most people, most internet properties, this is errors per second. For a logistics company, it might be the number of packages that arrived in a very poor shape. For the automotive industry, it's the number of safe cars, number of accidents where people walk away. Whatever that baseline is, you have to say, okay, this is what we're trying to improve, or this is what we're trying to achieve. And along the way, we have what we call stressor events. These are things that either radically increase that number or radically decrease that number. So if we're talking errors per second, you would see that value go up because errors are bad and going up is bad. Or if this is queries per second, you might see that this dips down and then recovers. Now, what's really important is that and then recovers part. So if we look at this and we say, okay, that's what's going on in our infrastructure. We hit a low, and then we come back up again. That come back up again is resilience engineering. A good example of this would be a load balancer. If I have a vanilla load balancer, something that's very boring and not smart, and I have 4 nodes behind that load balancer, if we're just doing round robin as part of our load balancing algorithm, when one of those nodes dies, it means that we're going to lose 25% of our requests. So we're going to dip down and stay low. That is not resilient. However, if part of that process or that system is to have your operations engineers recognize that the error is seen and pull that manually out of rotation, we'll have a very long trough, and then eventually it will come back up again. But the engineer that cycled that configuration is part of the resilient system. So the idea is, how do we reduce that as quickly as possible to not only identify when, but also recover from stressed states? A good example of this would be if we are going to talk about a commerce property. Let's assume that we take Alibaba and we extend that a little further. We've got an imaginary system. If I release a new piece of code, this new piece of code says, well, we're introducing a new index on our cache. That new index comes in, says, well, the old index is old. We're going to drop all of those old requests, all that old cache. But the SEO bots, the search engine optimization bots, are going to recognize that as being new, come in and smash your site, and then we're going to have some type of hardware failure. So as you're thinking about how all of this works, just understand that there are ebbs and flows to what that steady state is. Going down as part of the cache purge, well, that's bad. Going up as part of the SEO reset, also bad. Coming back down as part of the hardware failure, also bad. So I'm a site reliability engineer, and we see that we've been talking about resilience engineering. Now, in English, reliability and resilience, they sound very much alike, and there's a lot of overlap between the definitions. So how do we discuss the differences between reliability engineering and resilience engineering? If you think of this deviation from steady state as a sound wave, if you think of it where how far we deviate from the status quo is the amplitude, and then how often or the frequency of those issues is the frequency, then we can say reliability engineering is trying to focus on how often site issues happen. And resilience engineering is trying to focus on how large those events are when they happen. Going back to my example of the load balancer, a less resilient site is not going to load balance, but a more resilient site can say, okay, let's take that idea of the load balancer, and this time, let's add health checks. Very simple. If that port is open, if it's responding, if the queries coming back are acceptable, we consider that to be healthy. If it's not healthy, pull it out of the rotation and make sure that everything is okay. That creates a resilience assumption. We say, we're going to put this health check in, and we think when we experience our next event that something will be better than it was before. All resilience engineering does is create assumptions. It cannot by itself provide validation for those assumptions until a stressed event occurs. Now, chaos engineering, we don't want to wait until that event naturally occurs. We want to create the validation for that event. So, using something like Chaos Blade, we can come in, cut out that one node, and make sure that our load balancer does in fact operate as we expect it to do, and it can say, great, this is no longer a resilience assumption, it no longer represents risk, it is in fact a resilience implementation. This thing will in fact make our site more resilient. So this comes into a very nice cycle that we have back and forth with chaos engineering and resilience engineering. Chaos engineering creates the change, and by that change creates an assertion. Chaos engineering validates that assertion, and it says, yes, this is how it really behaves in production, or no, your change didn't actually work. Let's go ahead and make that change again. And then through the natural life cycle of all applications, that will change, an operation will change, and things will change, which will then we continue to validate that process. So to reiterate some more, resilience engineering attempts to improve how a system reacts to a stress state. Chaos engineering attempts to prove how a system operates during a stressed state. It's acceptable to understand that resilience engineering will create these new changes, but without the validation part, you're just operating off of assumptions. You're hoping that what you're doing is going to change. And if LinkedIn has taught me anything, hope is not a plan. All right, so as we start digging in deeper, that's what resilience engineering is. Now let's talk about how we can start doing chaos engineering. As we start to understand how these components work, it's important to understand, what are you trying to do? What are you trying to achieve? If I'm part of a logistics company, and what I'm trying to improve is the number of times a package arrives successfully to the doorstep of by the carrier, that's great. But if my job is to encourage more adoption of my system, well, that's not really the job of chaos engineering. What we're trying to understand is, what is your status quo, what is your steady state, and what are you trying to improve? For LinkedIn, when we looked at the other chaos engineering tools, most of them were focused on how do we improve the developer to create more resilient code. There are two really good ways that developers gain experience. The first one is by fire. How do we put these people in a position where they learn what site outages actually look like? That creates experience, and with that experience comes increased expertise. However, it's very common in my industry, in my area, that the average tenure of someone within these internet properties is anywhere between 2 and 4 years. What that tells me is that somebody coming into my site, trying to understand how to develop and work on my applications, is going to have a hard time, and they're going to make a lot of mistakes along the way as they learn the complexity of my site. However, the second way that developers gain experience is through intelligent tools, ways that we can convey experience that has been codified from other situations to say, the thing that you just tried to do will cause a site outage, and this is why. Then they learn from that component and no longer have to wait for something to go into production and fail. Now they can learn immediately as part of their pull requests what is going on and how things are stressed. But as we looked out across the infrastructure and we tried to figure out what could open source software do for us, the primary focus for us, or that software, looked like they were trying to prove how to make developers more skilled by exposing them to more side issues. That's not really our style. That's not how LinkedIn tries to do business. So how do we take that and up-level it? Well, the chaos engineering team decided that our primary goal was not to create developer friction, but to create a more resilient site. So this gave us a very interesting way to approach the problem. Instead of creating tools that shut things off, we wanted to create tools that could find the point or the intersection on our service graph where the relationship was not correct. And by relationship, I mean that the client depended on the server, but the server was not always there to be depended upon. So all of our changes that we created within our resilience engineering efforts happen at as low a layer as we can handle. When we identify that one of our front ends fails when our, let's go with our login flow, doesn't work correctly, and instead creates a bad experience to the user, instead of going and talking to that development team, we said, well, if there's one team that's making this mistake, surely there's at least 10 other teams that are also making that mistake. So instead of working with all of those individual teams, we would go and we would fix the library, fix the underlying component, and create post-commit checks to understand why that was failing and how we can improve that. So when you're thinking about what you're trying to improve or what you're trying to do with chaos engineering, it has to be more than we're doing it because my boss says it will attract talent. It has to be more tangible. You have to have a metric behind it. You have to be able to plan it out. This is the process that we go through whenever we're thinking about a new chaos engineering tool. This is how we try to understand what's working and what's not working. I'll go through this list with you to help you understand all of the subcomponents, as well as what's required to make things work well. Step 1, establish a steady state. I've described this several times. The picture that we've got here is of a barge, and on the side of barges, they have how deep in the water you're going. This is very useful because if you overload a barge, it sinks. That's bad. So that level doesn't necessarily mean good or bad, because if that barge were to, if we could see the 1 meter mark, that means that that barge is doing less work. But if we see it as going over the 7, 8, 9, 10 meter mark, well, that means it's doing far too much work. So I want to enforce with you that steady state doesn't represent everything's on fire. If your availability, or if your target for what you're delivering to your users is 82% successful, it doesn't mean that you've 18% failed. It means that you're 82% successful. That's it. That's the bar. Doesn't matter where the bar is, so as long as you understand where it is. I was talking about logistics before. However, I said the number of packages that arrive to the destination. This is also a difficult thing to achieve. Don't look at steady state as a simple integer. It is not the number of queries that we serve. It has to be of a rate of some kind. So if you look at the number of the rate of failure, the number of times the packages don't deliver, divided by the number of total packages that were attempted, that gives you a better understanding. Because if something happens and now you can no longer deliver packages, is that because of a system failure, or is that because of a business failure? If you see QPS drop on your site, is that because you have a routing problem, or is that because nobody wants to access your site anymore? It's been replaced by something different. You have to understand that there is a rate at which things are operating. Now, once you have that rate and you have a ratio between what is good and what is bad, it leads to the question, what is bad and what is good? The bad is, what does a failure look like? Using Alibaba as the commerce site, what does a failure look like? Does a failure look like an error on the page? Does a failure look like somebody clicked the button and was expecting a duck but received a cow in the mail? Like, what does failure actually look like? Do you have it codified? Do you have it well defined? Can you categorize your failures? Oftentimes we have HTTP as a way that we assert certain categories of failures. Everything from 0 to 199, the user should never see. That's part of normal communications with HTTP. 200 to 299, that means successful. The relationship between the client and the server seems to work out okay. 300 to 400, well, that's a little different. Sometimes that's okay. Sometimes that's really bad. We have some services that when they experience a failure, they return a 302. Well, that's not exactly what I asked for. I asked for a page, and instead you redirect me to the home page. Is that failure? Is that success? 400 to 499, also a category. If I were to say you as the audience are the client and I am the server, a 400 means that you gave me something wrong. That means you tried to authenticate, and that wasn't successful. It means you tried to access a page, and that wasn't successful. That means you've done something wrong. Except, if you think about it, if on the page that lists all the items I have for sale, and I click on one of those links, and it takes me to a 404, is that a you failure, or is that a me failure? Same thing with 500s. With 500s, that means that as the server, I've messed up. I've done something wrong. And it means that you, as the client, need to figure out what to do about it because what you've asked for may or may not have worked, right? So a 500 clearly means that I screwed up. Unless you consider I didn't expect you to send 65 emojis as your password, and I couldn't decode that. Well, is that you passing me bad data, or is that me not being able to handle Unicode? So when you go through these categories and you're categorizing what is good and what is bad, you really need to understand what the definitions are. And are they codified? Are they written down? We have a final catch-all at LinkedIn. If all of our monitoring has failed, if all of our alerting has failed, the last line of defense is our equivalent of WeChat angry texts. So that is how people can interact with the site. They try to access LinkedIn.com. Turns out it's not available. We've got some kind of routing issue in Germany. And they send to the Twitter, they say, hey, busted. That is a symbol of what is bad. The final endpoint, the final user has declared that this thing is not working. That is also a good metric of what is bad. Now that you've defined what's bad, figure out what is good. Do you have a definition of good? Are you measuring SLAs? Are you able to codify all of the events that this is successful? Your incident response and management system, however you handle incidents, is part of your distributed system. As I described before, the technician that shows up, restarts the configuration, and removes that bad node is part of your process. How well does that work? How often is that successful? How often does your system automatically understand that there is an issue and just take care of it? How frequently can your on-calls sleep through the night? There is a very good white paper out there called Lineage-Driven Fault Injection. Came out maybe 2 years ago. It's fantastic. Have a chance to read it, you should. But the idea is, if we start with what is working rather than what is broken, we start with what is working and we work our way back through every decision that was made. So in this instance, if I click the button that says that's the item I want in my commerce site, and then I click the button that says I want to check out, and then I click the button that says proceed, and then I receive the object. When I finally receive the object that I ordered, that's success. But all 4 of these steps are required for success. So if I want to figure out what I can do to test chaos and to test failure, then at any of those decision points, that's where I can start invoking failure. That's where I can start figuring out what's actually required. Now, lineage-driven fault injection breaks all of our resources down into 3 major categories. The first one, required. So, if we go back to this idea of here's the search page that shows me all my items, all of those items are required, right? Well, what does it take for me to be able to see all those items? Probably I'm reaching out to some search engine, whether it's internal or external, and trying to query to find out what items you care about. Now, I'm very much into rainbow unicorns. It happens to be what my family loves. So when I go to a website, I expect to see a full page of rainbow unicorns. You, not liking rainbow unicorns, but instead having a desire for pink elephants, you're going to see a bunch of pink elephants, right? That's how relevance is supposed to work. So when my request reaches out to that search engine and says, I need to show a request for Brian, if it can't figure out who I am or can't make the request, my page fails. So obviously, that's required, right? Well, not so much. Again, question what's happening here. If I can't make a request back to my search engine, should I fail the user experience? Or, as an option, can I show any kind of default data? Is there another system that I can reach out to that may have today's relevant information and query that and get that back? Which means I'm not relevant, but that's okay. I still have some items that may be of use to me at this moment. So that changes that search request from required to the second category, which is optional. And then the last category is auxiliary. So required absolutely has to happen for the user experience. and is supposed to cause a site outage or a user outage when it doesn't happen. Optional, it's really good if this happens. We should try. We should try really hard to do this, but it still doesn't impact the core member experience. And then auxiliary, which means nobody's going to know, or well, not nobody, but it means that the user request is not affected by this at all. This happens with tracking metrics, with event metrics, with system metrics, with logs. All of those kinds of components should not affect the user experience. The user should continue to receive those components, but we depend on them as operators. So as you start categorizing what is good and building your plan back all the way, you should be able to understand where decisions are made and when you can affect control. And that brings us to the control plane. Very often we talk about the control plane as where we make decisions, but in this aspect, I want you to abstract it just a little bit and consider where can you have impact. My team does not own any of the core libraries at LinkedIn. My team owns almost no code. We have a couple of chaos engineering tools, but when we want to change something, I go to that team and say, hey, we've got something within your library that we think is making a less resilient site. Will you help me change that? So my control is variable depending on my relationship with that development team and whether or not I can convince them of the importance of this. If you have control over when your application makes routing decisions, is it well informed of the health of the downstream systems? If you can affect that control, now you can start improving it. But also, that's the place where you can start making terrible chaos engineering choices, which is great because you can say, I want you to be convinced that this system that I have done something terrible with is absolutely something you should communicate to. And then find out if that hashing algorithm or that load balancing algorithm is going to be able to handle that routing. If your database is something that you're working with and you can't afford to let other users be affected by this, let's say you're in banking, right? Banking, we definitely don't want to start causing real outages because that means somebody standing buying a souvenir is going to get rejected from that payment. But what we want to make sure is that we simulate that failure. So here's a scenario. What if your application can identify that you, as an individual, are part of the internal team and therefore redirect you to another load balancer? That other load balancer is connected to a really crappy database. You're going to have a bad day, but that's okay because you opted into it. That choice of a client to understand where to send a request is really important. And that's by far the best control plane that you have to affect real change. How do your applications report health? Can you change the way that your applications report health so that when they drop off, it's a faster communication back to your load balancer? Can you leverage client-side load balancers with a gossip protocol? This is very similar to what HashiCorp is doing with Console. When one node is no longer behaving well, all of the upstream clients are informed about this behavior. That's good. Maybe it's not what you need, but it's definitely an idea. Safety third. As we're preparing, we've got the good, we've got the bad, we know what we're trying to change, we know how we're going to change it as far as the control plane is concerned, and now we have safety third. This comes from a very popular TV show in the United States called Dirty Jobs. It's run by an actor, his name is Mike Rowe. Now, Dirty Jobs goes with people who do really bad things. And by bad, I mean stuff that I don't have the Constitution for. The stuff that we absolutely need as a civilization to run, but man, I don't think I could get paid enough to do those kinds of jobs. So that would be oil riggers. Those guys, they do a really great job, but it is so dangerous. Or we have the individuals who work on the large wind turbines. I'm terrified of heights. There's absolutely no way I would get up there and do that thing. But we need people to do those jobs. So this safety third idea said, okay, the business, which is the TV show, needs to put you into harm. Nobody else is going to think about your safety. You are responsible for your safety. Because if safety was the first and only priority, we wouldn't even do the show. We have to be just a little dangerous. And I'm going to say something a little heretical to some of the operators out there. Reliability is not a required feature. Yes, reliability is a feature. A stable system costs money. If that system is, as I said before, a banking system, then spending the money on that reliability is absolutely important. But what if I'm a startup? What if I've got 5 people and I'm just trying to make sure that I can build an MVP? Tech debt is literally the definition of choosing features over operability so that we can, in the future, pay for that tech debt. When your tech debt becomes so large you can't quantify it, well, that means that you've gone in debt too far and you need to figure out how to work your way back. But strategic tech debt, being able to understand that safety is the third process, that's really useful. In the United States, at least, I'm not sure how it works here, but we often will take out a small measure of debt to buy a car. But that car gets us to our jobs, and with that job, we can pay off the car. When the car starts becoming too expensive that we can't afford it anymore, well, then we have to sell it and get a smaller car, or pay off our tech debt and focus on operability. With LinkedIn, we started using a process called linked out. That's our first chaos engineering tool. As we were thinking about how to make safety not a primary concern, but something that we wanted to focus on, what we were looking at is adding headers into the request. Headers disappear immediately. They're not stored anywhere. They're not logged anywhere. They're not persistent to the user session. And then propagating that header down along every single path. And this was really good because an individual user could interact with the site and say, I want to fail this particular endpoint, then ta-da, this is what your website looks like with that thing failed. That was us focusing on safety first. However, there was a question about how do we expand this out to the entire data center? We really shouldn't add these types of headers at our edge tier. We should find a better way to do it. So we started looking at our A/B testing platform. And our A/B testing platform, or feature flagging, depending on how you look at it, allows us to target individual members as part of their experience to the site and assert this thing is going to have a different experience than you would expect from other individuals. So I can opt you into a bad day. But as soon as we decided that this was a thing we were going to do, it became very clear that somebody, not understanding the mechanics of the system, could very quickly opt everybody on LinkedIn to a very bad day. So we built in safeguards, we built in double checks, and we built in systems where we could say, if everything goes poorly and the site disappears, we will know immediately. We hook into our SLA monitoring system, we hook into our availability, and we say during our chaos engineering tests, if something exceeds a certain threshold, abort everything and roll it back, whatever the thing was that we were doing. What's the least amount of work that you have to do to figure out what's wrong? When we started doing our version of Chaos Blade tests where we were affecting physical machines, as we were looking at the results, we understood that when we increased CPU pressure, it came out to the clients as network latency. When we increased disk pressure or delayed the I/O requests, it came out as network latency. When we removed that node from the cluster entirely, well, that was network unavailability. All of these things, at least within our infrastructure, were clearly network driven. So with linked out and with our fire drill, which is our Chaos Blade stuff, it was hard to say that the value of fire drill was very high because we could already emulate all of that from the client side. When we started trying to figure out, could we start disrupting the entire data center, we learned, at least through linked out tests, that our applications were not resilient enough to be able to handle this well yet. So we stopped working on FireDrill, and we went back to linked out, and we said, until we can get our applications to be comfortable with request level failure, we really don't need any of the larger level failure, because it's not going to get us anything that we don't already know. We had several teams come up with this. We use Zookeeper as our as an orchestrator for a lot of our applications, and we had several teams come up and we said, "Hey, we want to find out what happens when we take out Zookeeper." And I was like, "I know what's going to happen. Everything's going to go down. What's the value that we're gaining here by taking out Zookeeper? We already know that it's required for everything, so taking it down tells us what? That we were already right, that everything was already fragile?" Think about what you're trying to do with chaos engineering. What are you trying to improve? And do you need to start taking out a core router in order to prove what you wanted to do? And do not forget that when you have these resilience assumptions, you need to validate them. But I don't need you to take down the entire data center to prove if that's going to work. Maybe all you need to do is shift traffic frequently between data centers to prove that your DR strategies are sound. You don't need to wait for a lightning bolt to hit your San Antonio data center. You can say, this is the thing that we're going to do, and we're going to do it several times a day. Once you have that, you can say, okay, we feel pretty confident that this is going to work. And then you can take out the data center and say, yes, we're pretty good with this. Every layer that we've built within LinkedIn is small, incremental. We try to move just a little bit further every single time. We start with the developer, then the developer's team, then LinkedIn, and continue on until everyone is exposed to this issue, and it still works as expected. Whenever the SLA drops, or whenever we see that this site is not working as we expected it to work, we pull it back and we go back to the lower tiers and identify what went wrong, what went right, and how can we improve on the situation that we've got. Now, I left a couple of extra moments here for questions. Let me know what you got. Thank you.